Let P be a positive constant. We want to look at a series of the type the summation from 1 to infinity, 1 divided by n to the power p. Such a series is called a p series. We want to know for what values of p will such series converge and for what values of p will such series diverge. So we'll break this up into two cases. Case 1, we consider p greater than 0, less than or equal to 1. And case 2, we'll consider the rest of the possible values of p. P is greater than 1. In this video, we'll look at case 1 and show that any p series for which p is greater than 0, less than or equal to 1 diverges. And in the next video, we'll show that any p series for which p is greater than 1 converges. So suppose that p is greater than 0, less than or equal to 1. If p does equal to 1, then the series becomes the summation from 1 to infinity 1 over n. This is the harmonic series. And in a video right before this one, it was shown that such series diverges. So we took care of p equal to 1. Now all we have to do to finish case 1 is show that a p series for which p is greater than 0, strictly less than 1, diverges. Examples of such p series would be summation from 1 to infinity 1 divided by square root of n, and that is the summation n equals 1 to infinity 1 over n to the 1/2. This is a p series with p equal to 1/2. Another example would be summation n equals 1 to infinity 1 divided by n to the 0.86 power, in which case p is 0.86. It doesn't matter if it's a fraction or decimal. As long as it's strictly less than 1, such series will diverge. So before we actually verify this for arbitrary p between 0 and 1, let's look at one specific case. Look at this series, summation from 1 to infinity 1 divided by the cube root of n, which is the summation n equals 1 to infinity 1 divided by n to the 1/3. So this is a p series with p equal to 1/3. We're going to use the integral test to show that this series diverges. How does the integral test work? The integral test works like this. Suppose we have a series a sub n where each term is positive, and suppose we found a function. So let f of x be a function such that 4 conditions are satisfied. 1, f is continuous on the interval 1 to infinity. Now if the series starts at 2, then we would the interval we'd be interested in is 2 to infinity instead of 1 to infinity. Number 2, f of x is greater than 0 for all x in the interval 1 to infinity. The third condition, f is decreasing on the interval 1 to infinity. And the fourth condition is this: if n is 1, 2, 3, 4, 5, so in other words, if n is any positive integer and we take that n and plug it into the function, it will give us the nth term of our series. If all these 4 conditions are true, then the series n equals 1 to infinity a sub n and the improper integral from 1 to infinity of our function f of x either both converge or they both diverge. Now, if they both converge, they do not converge to the same value. This is not what the integral test says. So for our case, where our series is the summation from n equals 1 to infinity of 1 over n to the 1/3 power, if there's such a function, it has to be f of x equal to 1 divided by x to the 1/3 power. So this function is not continuous at 0, and everywhere else is continuous. Since the interval from 1 to infinity doesn't contain 0, this is true. If we take any value of x greater or equal to 1, it is positive. Plugging it in for x will also, the function will be positive. This function is decreasing because the bigger the x, the smaller 1 divided by x to the 1/3. We can also take the derivative and show that the derivative is negative. So in fact, we can do that. You don't have to do it. You can just examine the function. If the numerator is constant and the denominator gets larger with x, then the function gets smaller with x. But just in case, the derivative of this function is equal to minus 1/3 times x to the negative 2/3, which is equal to minus 1 over 3 times x to the 2/3, and this is less than 0 for x in the interval 1 to infinity. So this is a decreasing function. And then clearly, if we put in an integer, a positive integer for x into the function, we get the nth term of our series. So the function satisfies all 4 conditions in order for us to use the integral test. So we now evaluate the improper integral from 1 to infinity of 1 divided by x to the 1/3 power. And this is the integral from 1 to infinity x to the minus 1/3, which is equal to x to the 2/3 divided by 2/3, evaluated 1 to infinity, and that's the limit as x goes to infinity, 3/2 x to the 2/3 minus, when we plug in 1 for x, we get 3/2. Well, you can see that as x becomes larger and larger and larger, this limit is going to infinity. The integral diverges, so this improper integral diverges, and therefore the series from summation from 1 to infinity of 1 divided by n to the 1/3 also diverges by the integral test. So now let's turn our attention to any p series that looks like this: 1 divided by n to the p, where p is greater than 0, strictly less than 1. So we note, because of that, that 1 minus p is positive. If p is less than 1, then subtracting p from 1 will be a positive number. Now let f of x equal to 1 divided by x to the power p. This function satisfies all 4 conditions, just like 1 divided by x to the 1/3 power did. And so we can apply the integral test, and that means we can evaluate the improper integral from 1 to infinity of 1 divided by x to the p. Let's rewrite this as the integral from 1 to infinity of x to the minus p. And then when we integrate this, remember how integral works, we add 1. So this is minus p plus 1 divided by minus p plus 1, and this is evaluated from 1 to infinity. So this is equal to the limit as x approaches infinity. We have x to the 1 minus p divided by 1 minus p, and then when we plug in 1 for x, that gives us minus 1 divided by 1 minus p. Well, because 1 minus p is positive, that's important, this exponent here is greater than 0. Since p is less than 1, this limit will go to infinity, because any time we have x raised to any positive power, doesn't matter how small it is, when x becomes larger and larger and larger, x raised to that power will also become larger and larger and larger. Therefore, this limit is going to go to infinity, and the integral diverges. And because this integral diverges, we conclude that the p series of the form summation 1 to infinity 1 divided by n raised to the power p, where p is any value greater than 0, strictly less than 1, this series diverges by the integral test. And so in conclusion, any series of the form n equals 1 to infinity, 1 divided by n to the p, where p is greater than 0, less than or equal to 1, diverges. When p is 1, it's harmonic series. When p is strictly between 0 and 1, we just derive that result. For more videos, visit www.mathprepvideos.com.